well over a decade, the United States has had the capability to clearly record scenes such as these from polar orbiting photographic satellites. Of the many overhead camera systems used in recent years, perhaps no other has achieved the unique combination of wide area coverage, high resolution, and flexibility of operation than the one that captured these images. Here then is a historical look behind the scenes to show how this extremely complex camera in space evolved, and an appreciation of the government industry team that made it work at a level of efficiency and reliability seldom, if ever, equaled in the annals of space technology.
2, 1, 0.
Its name, Hexagon. The invaluable contributions of Hexagon to national security are underscored by General Eugene Tai, a former director of the Defense Intelligence Agency.
The Hexagon system was extraordinarily important to the defense intelligence business in general. You know, the broad requirements for a lot of intelligence from reconnaissance photography beside just installation intelligence. Targeting, for example, particularly nuclear targeting of very important target structures, the tracking of deployment areas, air bases, and so forth. And of course, today, tracking down mobile missile systems is terribly, terribly important. But I would suggest that the availability of broad area coverage was nothing short of miraculous for defense intelligence. And I'll never forget the significance of some of the installations that we found that had not been ever known before. Krasnoyarsk radar facility is an example. This huge installation had been under construction for a long time, and with the pinpointed and focused collection systems, of course, we weren't affording ourselves a broad area look that we got later from Hexagon, and were able to pick up things like that. I remember also we were concerned with whether or not the Soviets were pretty much doing away with the bomber business. And one of the key indicators that would indicate this would be the condition of their Arctic deployment bases, because in a staging way, they would stage aircraft out of these bases if they were going to strike the United States or North America. And it was quite a shock to the intelligence community to find out on Hexagon photography that they were maintaining and improving these bases steadily, and they were in excellent condition. Something that had just been taken for granted was not so, as we had no way to really sample these installations unless we did it on a focused basis. So broad area coverage that Hexagon provides is just absolutely essential. I think today also, of course, keeping track of the Soviet air forces in general, which during wartime as well as peacetime practicing will deploy from other than the regular air bases, from highway structures, and from, they've got aircraft landing gear that allow even their heavy bombers to land out in sodded fields, which certainly this country doesn't have. But keeping track of the movement of forces is terribly, terribly important. And of course, with broad area coverage, you can pick up such things as entire armies deployed. There's no way that you can do that if you were going to have to focus in on a little bit of it at a time. You couldn't afford it with a focused system. So it's going to be very, very important for a very long time. And as a matter of fact, I would say that the ability to get the broad area search that we get out of the Hexagon system may have been the most important intelligence contribution that's ever been made by a reconnaissance system to our foreign policy establishment. Terribly, terribly important. To say nothing of the mapping and the targeting and all those other structures that were supported with this system.
The achievements of Hexagon are better understood by a short glimpse back into the beginnings of modern aerial reconnaissance. Though the use of military aerial photography from aircraft had spanned 2 world wars and the Korean conflict, it was not until the early 1950s that a series of major events within the Soviet Union motivated American military planners to search for new ways to keep abreast of military developments and strategies behind the so-called Iron Curtain. The first of these events was the detonation of the first Soviet H-bomb in August 1953, which followed by only 9 months the first test of this country's hydrogen bomb. Then, in October 1957, the Soviets launched Sputnik 1. The implication of these 2 events was quickly recognized by those in charge of U.S. defenses. Quite simply, it meant that the Soviet Union not only had a thermonuclear weapon, but also the large rockets needed to deliver it over intercontinental distances. For America's intelligence community, the collection of detailed, up-to-date information on this new awesome weapon of mass destruction became a task of the highest priority. Meanwhile, the United States moved ahead with the development of its own long-range missiles in the mid-1950s, a capability that would, in time, also play a critical role in photo intelligence. By the late 1950s, this country had developed and successfully deployed the U-2 aircraft, which provided much valuable photo intelligence during the decade. Unfortunately, in 1960, a U-2 piloted by Francis Gary Powers was downed as it attempted the first one-way traverse of Soviet territory. Though the well-publicized event closed Russian skies to American surveillance aircraft, it gave added incentive to the development of Earth-orbiting satellites for photo reconnaissance, an activity that had been initiated some 4 years earlier. Giving weight to the optimism for this approach was the fact that the ground rules for space vehicle operations had not yet been defined. In 1956, the U.S. Air Force established a forward-looking development plan for what would become a family of satellite systems to collect various types of intelligence, including photographic coverage of denied areas.
Only resource then was closed.
Bud Whelan recalls how events gave impetus to this effort under the name Discoverer.
It was a joint Air Force-CIA project directed by Eisenhower as an interim step, while SAMOS, a very much more ambitious program, had a chance to come to maturity. But the President, under advice from his advisors, had directed that a simple program, a less ambitious program that could get some film in a hurry, be developed. And it was a frustrating program. I think there were 13 failures in a row before that first success of Corona. Interestingly enough, that first bucket of film was returned as Gary Powers sat in the dock in Moscow being sentenced for espionage, and one of those remarkable coincidences. And so Corona came into action just as Powers went out of action, and with far more sweep and power.
The pioneering Corona system required physical recovery of its film payload from orbit, a capability that was successfully demonstrated for the first time in history in August 1960. In large measure, it was the success of Corona that prompted both the CIA and the Secretary of the Air Force Special Projects Office to independently launch a number of feasibility studies for the development of a new generation search and surveillance system.
The requirement for Hexagon originated by a recognition in 1963 that the success of Corona and Gambit led to a conviction among intelligence analysts that the country really needed a system that would have the resolution of the Gambit system and the area coverage of Corona. Therefore, both the Special Projects Organization and the Central Intelligence Agency conducted studies of a system that might meet those very demanding requirements. The Special Projects approach was known as S2 and was aimed at a system that would have about 3 to 4 feet resolution and 150 miles swath coverage. The Central Intelligence Agency's approach was known as Fulcrum and had a little bit better resolution but very wide area coverage as well. The competition was a very tough one and was controversial, primarily because the technological demands of a system with those remarkable capabilities were really tremendous. As a matter of fact, there were some who doubted that it really could be done, and that a better approach might be to improve the Corona system to somewhat better resolution and to continue Gambit as a surveillance system. But as the time went on and there was substantial support for research to confirm design ideas and for the pre-design work, there developed a conviction that one could indeed build a system that would have this remarkable set of capabilities, the resolution of Gambit and the area coverage of Corona.
The Central Intelligence Agency had formulated plans for such a synoptic camera. It had nearly the same specifications as the proposed Air Force system. Thus, a high-level decision was made to cancel both CIA and Air Force efforts and establish Hexagon under the direction of the National Reconnaissance Office. Some of the key participants recall certain events of that period.
The answer that came out of the drill committee was that a really significant improvement in the resolution of the search system was possible. Not a modest improvement, but a big improvement. And they rendered their report then early in February, I think, 1964, to McCone and me, and identified a number of problems, but said these are things that we ought to begin working on.
Lou Allen has described beautifully the requirement as it was given to CIA and the Air Force by the intelligence community to build a system with Corona's broad area coverage and Gambit's high resolution. This was not an easy task, as he pointed out, and those of us who had been associated with the development of the camera system were quite anxious as we began the evaluation of the initial film back from Hexagon to see how well we had done in meeting our objective. The National Photographic Interpretation Center prepared for us a standardized sample of Gambit imagery, which we could use for that evaluation. And during the first performance evaluation team meeting, we were quite pleased to find that we had indeed met the objective that we started out to meet. The camera system for Hexagon is a very complex device, one that is a little bit too difficult really to describe in words. But one of the things that made that device work so well was the fact that you could interface an oscillating platen assembly with a high-speed film transport to a rotating optical bar. The device that allowed this to happen, called a twister, was one of the few things that I think in my career I would like to categorize as a true invention by one of the contractors. As we initially envisioned the Hexagon camera system or sensor system, it was to be a somewhat separate segment of the Hexagon program. It soon became clear, however, that an integrated design would be necessary in order for us to meet the objectives, and from that decision we saw develop a very effective government contractor team that put together the overall system for the government. That what we are going to hear from now are some of the key players of that team to get some other views on what they saw as the issues at the time.
The agency program office and the special project program office developed their own specific specifications for their parts of the system. Starting in April of '66, these separate offices then conducted competitor selections, competitor competitions, and source selections to determine which contractors would participate in the program.
The principal problem in an optical system in space is the thermal problem. The upper part of the optical system normally sees cold space, and the lower part sees the warm Earth. But in this system, the optical systems rotate continuously, and therefore are bathed such as a rotisserie in the thermal environment. In addition, there are two optical systems which rotate in opposite directions, and therefore the angular momentum is canceled, and this is of great advantage to a space vehicle. A second major development, which was already in hand at the time, was the optical design of the system. Eastman Kodak Company had developed some very high-resolution film, which was very attractive for this purpose, because you could pack a large amount of information into a small area and therefore a small weight. The optical system had to have a long focal length. It turned out to be about 5 feet, and had to be fast. It was F3. Again, I repeat that all of these were in hand when the program started at that time.
Well, we were coming, of course, from our Agena Discover Corona program, and we're attempting to take a great deal of advantage of our experience there. In addition, because of the impositions of the payload, we had a large power demand, and with the long time on orbit, we had to develop the largest solar array system that would be in operation at that time. We also imposed a test philosophy that subject the vehicle to the type of environment it would see in ascent and also on orbit, and this required acoustic chamber to simulate the ascent environment. It required a thermal vacuum chamber with capability of optical measurements to simulate the on-orbit environment. In addition, as Rod has mentioned, thermal control and influence is of tremendous importance to a payload like this. And because of the very long structure we had to develop controls that would inhibit misalignment and assure accuracy for the film pass as well as the camera. And this was indeed a technology challenge.
As the RFP came out for two versions of the recovery vehicles, one with 2 vehicles and one with 4, 2 large vehicles and 4 fairly large ones. And we were happy to see that when the go-ahead was issued, it was with for the 4-vehicle version because it made the recovery problems for us somewhat easier. Our previous experience had been with deployment of the main parachute in, say, the Mercury and the Gemini programs at quite a low altitude, 10,000 feet. Well, with this program, the main chute deployed at 50,000, and it had to be tested at that altitude. And the test range at Salton Sea and El Centro was a considerable weather and scheduling problem, and we would suffer delays of sometimes weeks in between drops to get the test data for the continued development of the recovery system that included, by the way, not only the main chute, but the drogue chute.
In 1966, efforts were made then to develop a mapping camera which could be flown on Hexagon. HITEC, through a source selection board, won the competition, and a 12-inch focal length camera was developed with a train camera and 2 10-inch focal length stellar cameras. The camera used 9.5-inch film for the train and 70mm film for the stellar cameras. This camera flew on Hexagon, starting with mission 1205 for 12 missions thereafter. It had high resolution for a mapping camera, low distortion, and was used considerably just by itself for map making. But combined with the, as an attitude determination device, combined with the high resolution film from the panoramic system, then it was used quite successfully for mapping.
The agency picked up the work that had been done at ITEC and went to PerkinElmer. PerkinElmer quite fortuitously had an idea for doing the film transport. And when you put together the ITEC work that had been done to that date on government funding, and therefore belonged to the government, with the developments that had gone on quite coincidentally at PerkinElmer, and put them together, you had a system that really began to make a lot of sense. That combined solution was taken to Dinland in his office in Cambridge. I myself took it, and he said, by golly, I think this thing's really going to work. And he so reported to Vance and to McCone, and at that point then the system went forward.
In 1966, the Hexagon program had reached the formal competition stage, and both the CIA and the Air Force established program offices. The contractor team finally selected consisted of the PerkinElmer Corporation, which would develop the prime sensor or dual camera payloads. Lockheed Missile and Space Company would build the basic structure for the entire satellite vehicle and would also serve as final test and integration contractor for the satellite basic assembly. McDonnell Douglas Astronautics Company to design and build the large re-entry vehicles used to return the exposed film loads from orbit. General Electric, who would build the Mark V re-entry vehicles in which film from the ITEC mapping camera system would be returned separately from space. The ITEC Company, to be responsible for manufacturing, testing, and operating the precision mapping camera system for accurate positioning data. The Eastman Kodak Company, to produce and process the various ultra-thin base black and white and color films for both the prime stereo cameras and the mapping camera system. The Martin Marietta Corporation would provide the liquid-fueled Titan 3D launch vehicles, and the United Technology Corporation would furnish the solid rocket motors needed to launch the 10-foot diameter Hexagon satellite vehicle. And TRW Systems would write the T-Unity software programs that would be needed to control the many satellite orbital functions and operations. The development of the Hexagon system was an ambitious program requiring the solving of many formidable engineering problems. The entire launch vehicle would weigh nearly 1.5 million pounds and stand 160 feet tall. The satellite vehicle would consist of 3 sections. The aft section housing the control systems, electrical distribution and power, and the telemetry, tracking, and command systems. The midsection containing the dual panoramic camera assembly, the film supply, pneumatics, and electric supply. And the forward section containing the 4 film recovery vehicles, the mapping camera, and its re-entry vehicle and sub-satellites. The length of the film path from each supply assembly through each camera system and into the first recovery vehicle is almost 100 feet. Each supply assembly provides 150,000 feet of film to each camera at controlled constant velocities of up to 70 inches per second under specified tension. The looper assembly in each film path serves as the interface between the coarse and fine film transport systems and allows the total length of the film stored in it to be constant. This enables the fine film transport system to supply film at speeds up to the 200 inches per second required at the camera's focal plane. The dual camera assembly contains a pair of rotating panoramic cameras. One camera looks forward of the satellite vehicle and the other looks aft. Each camera has a 60-inch focal length and f3 folded optics. The optical system, which contains both reflecting and refracting elements, is mounted in a cylindrical housing called the optical bar. Light enters the aperture of the corrector plate, is reflected off the folding flat onto the 24-inch primary mirror. The primary mirror focuses the light back through the field group mounted in the folding flat center hole and then onto the film focal plane. During photography, the optical bars rotate continuously through 360 degrees to provide cross-track scanning, but photography actually occurs only between 30 degrees and 120 degrees of each rotation. In each optical bar, a platen which directs the film across the focal plane is electronically locked to the optical bar through 130 degrees of scan. Each camera system contains active steerers and passive articulators to center the film on supporting rollers at critical points in the film path. Dual take-up assemblies in each of the 4 re-entry vehicles have a film capacity of 1/4 of the supply film load. Prior to Hexagon, no other satellite camera system had been called upon to transport very large quantities of ultra-thin base film at speeds of over 200 inches per second and be able to reverse direction both at the take-up and supply spools. From its very first mission, the highly complex system fulfilled performance objectives as explained by one who managed Hexagon for many years.
The fact that this has been accomplished without any major modifications to the overall system attests to the soundness of the original concept design that was implemented on the program.
I attribute this phenomenal on-orbit performance record to two basic program principles. The first being the redundancy that was built into the system design, the second being the unique and comprehensive factory-to-pad testing that was rigidly implemented and enforced on the program. System redundancy, where practical, was designed into all critical elements and subsystems so that the failure of one single component would not result in a catastrophic on-orbit mission failure.
Hexagon launches conducted during the program's final years differ little from the system's first launch on 15 June 1971. Then, as now, the satellite vehicle arrives on schedule. Pre-launch checkout is uneventful and routine. And booster performance is nominal from liftoff to insertion of the payload in orbit. What was different back in 1971 was the fact that it had taken 5 difficult years to carry Hexagon from program approval to first flight, for the sophisticated engineering of Hexagon represented the leading edge of photographic satellite technology at that time. However, the products of its high resolution, wide-angle stereo cameras, and 12-inch mapping camera more than justified the time and cost of its development. Traveling in its 95-mile-high near-polar orbit, Hexagon has been able to fulfill the search requirements of the intelligence community by scanning and mapping millions of square miles of Soviet-controlled terrain. It also exceeded the requirement of a surveillance resolution of better than 3 feet, a capability essential to verifying arms limitation agreements. Though impossible to display here in standard motion picture film, stereo photography from Hexagon also provided its worth many times over to image analysts and the user community. However, quality imagery such as this, produced in vast quantities by Hexagon, could not have been attained without its ground-based guardians at the Air Force Satellite Control Facility in Sunnyvale, California. In this center, the hub of a global satellite communication network, Air Force and contractor personnel maintain a constant electronic dialogue with the Hexagon satellite. Through voice and telemetry links, Hexagon's mission controllers continually monitor how the vehicle and its payload systems are working and transmit to it any corrections required to control the vehicle. The center's computer complex and the T-Unity software program help to determine the specific mission profile that will best fulfill planned intelligence collection requirements. Toward this objective, cloud cover data from the Defense Meteorological Satellite System is also used to schedule photography for maximum yield over targeted areas. This optimizes film utilization. Uppermost in everyone's mind during a mission is the fact that once separated from the Hexagon satellite, a re-entry vehicle is on its own and must operate flawlessly till its vital cargo of exposed film is caught in midair by a C-130 aircraft and then rushed to the special processing facility. To verify on-orbit performance of the system, interim reports concerning film payloads as they are recovered are transmitted immediately by a post-flight analysis team to Hexagon's mission controllers. This data enables critical corrective actions to be taken. For over a decade, Hexagon's wide-angle stereo cameras continue to sweep vast areas of denied terrain, freezing in time such wide-ranging events as an entire order of battle. For example, a major war in the Middle East, or the conflict over the Falkland Islands. Supplementing and supporting this prime function during 12 missions was Hexagon's mapping and geodetic capabilities, first with the mapping camera and later with the solid-state stellar sensor. Mapping, charting, and geodesy also played very important roles in the success of the Hexagon program.
During the life of this system, we acquired several tens of millions of square nautical miles of coverage, which was of high mapping quality. During that time, we acquired approximately 98% of the Eurasian landmass. We got 75 to 80% of Africa, the more significant point being that approximately half of the cloud belt was acquired for the first time under any mission. We also acquired much of the southern portions of South America, which was vital to our program for 1 to 250,000 scale maps of that area. In addition to the maps, we were also able to produce several 100,000 points that were critical to the Strategic Air Command for target positioning, for offset aim points, radar fixed points, and the like. In coordination with the operational community, the Defense Mapping Agency assisted in the development of a solid-state stellar device, which would enable the panoramic camera's attitude at the instant of exposure to be determined with a high precision by filming the star fields.
We have seen the abundant legacy that Hexagon has bestowed on both the intelligence, mapping, and charting communities. To summarize how this advanced system was made to yield increasing harvests of data, here is Colonel Larry Kress, Hexagon Program Manager.
The first Hexagon mission illustrated the thoroughness of the design, the test, and the integration work. The mission itself, on its first launch, worked as planned. The goal was for a 30-day mission, and the eventual goal was for 45 days on orbit. All the functional problems had been worked out in the test laboratories and the production facilities. The first mission lasted 31 days, active mission, and was extended for 21 additional days for the solo or engineering period, thereby giving us time to check out how well the basic systems work. I think reaching that goal gave us a start then for what illustrated a very good fact, that the design was solid and that all the work had been done. But it allowed us then to go on with evolutionary changes over the 14 years that we've flown so far, to make small changes to things like the housekeeping functions, improving thrusters, for example, improving the basic electrical design. As well, we were able to improve the camera system and the films. The cameras became more efficient, we operated them more efficiently, and as newer film types came along, we were able to put more film on the system, and we're also able to get better resolution through better grain structures on the films. An additional thing that has been very good about this program is the ability to carry auxiliary payloads into orbit on their own, where they could not have had an easy way to get into space otherwise. Over 9 tons of auxiliary payloads have been carried into space on board the Hexagon missions. The first mission got the best ground resolve distance of 2 feet and had an average of 3.5 feet. Today's missions are down to an average of 1.9 feet ground resolve distance in its imagery. In addition to that, we have grown from the original flight, where we gathered 8 million square nautical miles of cloud-free imagery from the ground. We're now up to 28 million square nautical miles of cloud-free imagery today.
For an overall appraisal of how important Hexagon has been to the United States during the 1970s and early 1980s, we turn to Major General Ralph H. Jacobson, Director of the Secretary of the Air Force Special Projects Office.
The high-quality technical information Hexagon has provided for the past 15 years has enabled our country's leaders to make diplomatic and military decisions vital to the survival of America and the rest of the non-communist world. In a time of deepening distrust between ourselves and our adversaries, Hexagon has provided us solid visual evidence of treaty compliance or violation by the Soviets, thus enabling us to enter arms limitation agreements with confidence and safety. Hexagon has also helped us bolster our own defensive forces. Its mapping ability has enabled us to locate enemy targets with sufficient accuracy that they may be held at risk with our own strategic forces. In summary, Hexagon has more than lived up to the expectations set for it in the mid-1960s. Its panoramic cameras have recorded vast areas with the resolution necessary to fulfill its charter as our primary search and surveillance system.
The panoramic stereoscopic eyes of Hexagon have indeed provided the eternal vigilance, which is still the price of liberty. For that accomplishment, we must thank the dedicated team of government and contractor people, the scientists, the engineers, the mission controllers, the image analysts, all working together to show once again the technological achievements that a free people can attain in the preservation of freedom.
5, 4, 3, 2, 1.
Hexagon, Sentinel of Liberty.